Hi everyone. This is an extra video to review everything we discussed in terms of interference in topic 4 and 9. Actually, the two slits case is the only section from topic 4. Everything else is from the wave phenomena unit, the HL extension. I know how things get confusing as we discuss more and more cases. So I hope this summary video will help in terms of straightening out some confusion. So let's go. The first case we discussed, we did this in the core unit topic 4, two-source interference. Now, in this situation, we have two sources which are assumed to be point sources. So if a question does not give you width or tells you that they are point sources, in some way or another, the question describes these as points, dots made on a opaque screen or something. We treat them as point sources with no width at all, where diffraction effects are ignored. This is an ideal case. In this case, we derived this formula, you will remember from the interference lesson, and the path difference n lambda is constructive, n plus a half lambda is destructive, and there's constant intensity when there's no diffraction effect. So this is the important bit here. You see that all of these intensities of the center, first and second maxima on either side is simply constant. And the other important detail here is that the angle that we use to derive the formula is the angle that stretches to the first maximum. Now the second case we discussed was single slit diffraction. We have a whole big gap and we derived this formula in the lesson. This angle here is the angle that stretches to the first minimum, from the center to the first minimum. And the ratio that applies y over d equals lambda over b, that's half the width of central bright. So if you're asked to calculate the width of the central max, it would be asking this whole thing, which would be 2y. And the other important thing here is to know that the intensity of the next max, which is this, or this, should be much smaller than the central max. Combination of the two slits with diffraction effects of known width. Now, if we're given the width of the two slits, which are not point sources anymore, we cannot ignore the diffraction effects, which means the angle is still that measures to the first maximum, but the intensity is not constant. So we call that the diffraction envelope, and the intensity, as we look away from the central line, would decrease, staying in the envelope. So the location would be the same for the first maximum if these were point sources. If they're not point sources, if they are individual single slits, we would have the first maximum centered at the same location, but with less intensity, and it would stay in this diffraction envelope. If I increase the number of slits centered around the same point, the calculation wouldn't change. So again, the locations of the maxima would be the same, but when we increase the slits of equal width and equal separation, we would have brighter and narrower fringes as we increase the number of slits. So this I just showed you with 4 slits here. These small ones in between the major maxima are not important mathematically. You wouldn't need to measure the location or the intensity of those ones, but they will be there, smaller maxima, but the main interference maxima where we have a bright fringe would be at the location where the maxima would be for 2 slits or 3 slits or 4. This is the case where we have, again, identical slits with constant separation. So we're simply adding more slits, identical slits, to what we already have, and the effect is to have brighter and narrower fringes. To compare, I'll go back to the last one, you see I intentionally made this intensity, this size a bit smaller. So when I increase it, you see these are wide and intense as that much. And when I go back to this, the 4-slit case, they become more intense overall, still within the single slit diffraction envelope, and they each became narrower and brighter. Okay, the next case we discussed was the diffraction grating. In this case, we're not adding identical slits, we're splitting the same space into smaller and smaller and smaller pieces. So if I have n number of lines per meter, 1 over that would give us the d, which is the separation of consecutive slits. The diffraction grating formula is here, where theta is not small enough to be approximated to 0, so we don't equate theta to sine theta. We keep this as sine theta, and n is the order of maxima. So the angle we calculate to n equals 1 and the angle we calculate to n equals 2 would work around this formula. Again, the angle here is from the center to the first maximum. And obviously the intensity decreases as n increases. So n equals 2 would be less bright than n equals 1, which would be less bright than the center, etc. In some questions, the question asks you, given a d and a lambda, asking for how many bright fringes would be seen on the screen. In that case, you're looking at the maximum number you could see within this range and that range. The theta you would substitute would be 90 to find the maximum number, which would give you the n on either side of the center. You have to double that for the two sides and add the one at the center to find the total number of maxima seen on the screen. And don't forget that all of the lengths in any of these formulas must always be converted to meters. So if you're given number of lines per millimeter, don't forget to change that to number of lines per meter, basically multiplying the number of lines by 1,000 to know how many you would have in 1 meter. And then 1 over that would give you the d in meters. That brings us to resolution. We have 3 cases we discussed: well resolved, just resolved, and not resolved. Well, the just resolved case follows the Rayleigh criteria. You have 1.22 lambda over b formula in the data booklet. When that's equal to d over d, the lowercase d being the separation of the 2 points or sources being resolved, and the capital D always the distance to the sources from the screen or aperture. The B here is the diameter, not radius, diameter of the aperture. And the angle here is the angle that is the whole angle between these two rays. Not from the center, it's actually the whole angle this time. And if this ratio is smaller than that ratio, the images would be well resolved. This would be the intensity diagram, and this would be what we would see. If that ratio is larger than that ratio, then the intensity maxima are too close. We cannot resolve those two images. So in questions, you should look for ways to make that ratio smaller for a more resolved, better resolved, well resolved situation. And if that ratio is becoming smaller for any reason than that one, then the image is not resolved anymore. In the case of determining the resolvance of diffraction grating, we defined the capital N first as the number of lines illuminated. So if that's the width of my beam and I'm using n number of lines per millimeter, the width of the beam divided by the number of lines per millimeter would give me how many lines my beam is passing through. So if I have a 2 millimeter beam and 100 lines per millimeter, I would be illuminating 200 lines. So this capital N is 200 in the formula. M in this formula is now the order of maxima. Since the number of lines eliminated is represented with an N, the order of maxima is now represented with M in this case. And as usual, the center is M equals 0 and 1 and 2 and so on as we move away from the center. And the R is the resolvence factor of a diffraction grating. It's the ratio of the average wavelength that is incident to the wavelength range that can be resolved within this diffraction grating at M equals 1 and at M equals 2. Now, to understand what this means, I can say further from the center, basically as M increases, the delta lambda would mathematically decrease. You can see this from the formula already. And that means a smaller wavelength range can be resolved. So you can tell smaller, closer wavelengths apart. If resolvence factor is small, you can't resolve close wavelengths very well. But if you have a resolvence factor that is very high, that means you can easily resolve closer wavelengths, which means you would have a more clear image. This is an example of white light going through diffraction grating. If white light is incident on a diffraction grating, the central bright will always be white because that is a maximum, a constructive interference point for any wavelength in white light. So let's say if I'm using 80 lines per millimeter, this would be my central maximum, which is white. This would be my first, blue on the inside, red on the outside. And this would be my second order, symmetric on both sides. If I was using a diffraction grating with 100 lines per millimeter, these bright maxima would be further from the center line, but still blue on the inside and red on the outside always. If I was using 300 lines per millimeter diffraction grating, I may not even be able to see the second order maxima because the pattern would get wider and wider, meaning the angle to the first maxima would be increasing. So the angle on the 80 would be that, the angle on the 100 would be that, and the angle on the 300 would be that angle. The angle always to the maximum. The last thing I'm going to discuss in this video is thin film interference. First medium is air, let's say n equals 1. Second medium, which would be the film that is coating over the third medium. So if the second medium has a refractive index of 1.6 and the third medium having a refractive index of 1.3. Now, what we see is the reflection. So this represents the incident ray. Remember that when light reflects from a heavier medium, it goes through a phase change because it acts as a fixed end reflection. So that would definitely be a fixed end reflection because this ray is reflecting off a medium which has a higher refractive index. So this is the first ray that is reflected that will interfere in my eyes. The ray continues in the second medium and that part reflects off the bottom end, which acts as a free end reflection because this third medium has a smaller refractive index than this second medium. So this reflection is a free end reflection. Some of the ray continues in the third medium. We're not really interested in that. We're interested in this reflection, and it goes out and interferes with this first one. These are the two rays that form the image in our eyes. One of them has gone through a phase difference and the other one has not, which means there's a pi phase difference between them. To represent what that looks like, this would be similar to the diagram we used in the two-source interference lesson. If there's a crest leaving this point at an instant and another slit which has a phase difference of pi, this is releasing a trough because they are already pi out of phase. If they interfere at this point where the path difference is lambda over 2, you would remember from two-source interference that if the path difference is half lambda, that would be a destructive interference point. But now this is a constructive interference point, and here is why. If the path difference is lambda over 2, that's where we would show it on the diagram. So that is half a wavelength. So if that is a trough right there at this instant, half a lambda later, this is a crest. So crest here and crest here, they will travel the same distance after this point and cause a constructive interference point when the path difference is half lambda. If that path difference was 1 lambda, the trough 1 lambda later would still be a trough and would interfere with a crest on the pattern, which means that would be a destructive interference point. To summarize, n lambda path difference means destructive interference, n plus a half lambda means constructive interference. However, if the third medium has a refractive index which is even higher than the second medium, then we would have that point also reflecting as a fixed end, meaning that these two rays that are interfering in our eyes are now both pi out of phase with the incident, but they are now in phase with each other. So both have a trough being released. So if the path difference is half lambda, the trough and a crest would interfere on the pattern, meaning that's a destructive interference point. If the path difference is 0, that is equal distance from two sources, a trough and a trough or a crest and a crest would interfere, making this point a constructive interference point, which means we go back to the original calculation. Thin films look colored because if this is white light, the different wavelengths would have their constructive interferences at different angles, which means if this is white light, there would be a slightly different point of maxima for different wavelengths. So basically, when we see the colors separately, what we're actually seeing is the different locations for the constructive interference for each wavelength. So that ends my summary. Thank you.